So a couple of months ago, I was cruising on Nature Publications looking for an interesting paper to read because I had some downtime at the time, and I came across a very interesting paper. The paper was titled Community Detection with Node Attributes in Multi-Layer Networks. I didn't really think the title was that sexy. I didn't think that it was a paper that I was going to read, but as I looked at the page, I noticed that there was a tag on this paper called Social Physics. What the hell was social physics? I've never heard of this before. I've heard of quantum chromodynamics, I've heard of quantum field theory, I've been doing a lot of GR, I've been doing a lot of biophysics, my PhD work was in biophysics and all this, but I've never heard of social physics. What was social physics? So I dove deeper into this notion by reading the paper. And when I read the paper, it was very confusing at first, so I had to go through it a couple of times. But something quite profound stuck out to me. And that thing that was quite profound was this matrix equation right here. Now, on the face of it, this looks like a complex equation. But as I looked more into the paper, I found that this was actually quite profound. This is an iterative equation. And what it did is it said, we're going to take something called a design matrix, and we're going to take something called an adjacency matrix. And an adjacency matrix is something that I've heard of before. An adjacency matrix is something that can actually be used in chemical systems, where you can describe how adjacent one atom is to another. And so you can sort of think of a chemical system, if you will, as a graph, where each node in the graph is an atom and each edge in the graph is a bond. Now, the strength of the bond between two atoms can be quantified as being a double bond, a single bond, or a triple bond. And you can actually you can put a number to that, and that would be an entry in this matrix. So take, for example, a matrix that looks like this, and two nodes. So you have node 1 and node 2 in this matrix. You find the cross point in this matrix, and you put a number in that matrix corresponding to the row and the column of those two items, or those two atoms. And the number in that matrix you could say is a 1, a 2, or a 3. If it's a 1, you have a single bond. If it's a 2, you have a double bond. And if it's a 3, you have a triple bond. So you can construct a matrix for any number of chemicals, if you will, that describes how close atoms are to one another in terms of the number of bonds that exist between any two atoms in that molecule. Okay, but what about social physics? Where did this have to play a role in social physics? Well, as I read more into the paper, what I found was that you can sort of think of groups or communities, if you will, as consisting of nodes, and each node represents a person in that community. Now, the strength of the connection between two people within that community can be quantified by the adjacency matrix. And then you have something called the design matrix. The design matrix is a little bit different. The design matrix will tell you what kind of attributes those people have. Say, for example, you are living in a Republican community, and those attributes might include a love for guns, for example, or a weakened centralized government, or weakened abortion laws. When you couple these two matrices with two other matrices that the paper actually outlines and defines, what you get in the end is a matrix that represents the probability of a person going from one group to the other. So suppose, again, you're a Republican, and you really like the Republican ideals. You really like the notion of a weakened government, and you really like the idea of a strengthened Second Amendment. Okay? And you have a group of people as well that agree with you and your sentiment. Your community also likes this. Now, if your community also likes these principles, then that is going to be a very tight-knit community, and the probability of you leaving that community is going to be very low. And so entries in this matrix for each person is going to be relatively high. Now, the only stipulation, if you will, or boundary condition, if you will, on these matrices is going to be that the rows sum to 1. So for each matrix, we're going to have two columns. Each row is going to represent the person, and each column is going to represent the community. And so every point in the matrix is going to represent the probability that one person is going to be in that community. And we need two of these matrices. One matrix is going to be the outgoing matrix. This is the probability by which someone is going to leave the community. And the other matrix is going to be the probability by which someone enters that same community. So it's, in one way, we could sort of think of this as I'm being pulled away from the Republican Party, for example, by the things that I don't like about the Republican Party. Or I can think of this as I am being attracted to the Democrat Party by things that I like about them. So there's two things that we need to take into account when we're considering the motion of any node between two communities. One is what's repelling them away from the community that they originated in, and the other is what are the attractive forces that's bringing them towards the community that they're entering. That's why we need two matrices. And so at the end of the day, what you end up getting is an equation that tells you something about how to update the probabilities based off of the attributes, right? The attributes of each node. That's going to be, again, the intrinsic attributes of each node. Kind of like spin for a fundamental particle. For a fundamental person, if you will, you have something that really likes centralized government, really hates abortion, and really loves Second Amendment rights. And that's going to be codified in the design matrix. That's this X matrix. Whereas in the adjacency matrix, that's just going to tell you everything you need to know about the connectivity between both nodes. So as long as you have these two matrices, you are able to then update the probability matrix. Now the big question is, as you iteratively update this probability matrix, is there a point that reaches equilibrium? Now this gets into a lot of very interesting stuff, and I'm not going to get too much into the details, but I've created an animation right here to show that there is indeed, that you can actually find a set of matrices that finds equilibrium eventually. Okay, and now if you want to get deeper into the math of this, I do have a video coming out, and I'm going to go deep into the math. If you want to get the notes on this, I'm also going to be selling the notes to this on my Patreon. I don't want to scare you guys with a lot of math here because this is a short video, but this is all to say that social physics actually is a thing. This is actually something that's quite interesting. It tells us the dynamics of communities and how they're more likely to leave and rejoin other communities. And so in one sense, you can think of this as multi-layered networks that are dynamic. And all the dynamics is codified in these matrices. So this is actually very, very interesting stuff. And it can be directly applied to chemical systems as well. And even chemical systems when it comes to understanding design for chemical drugs, for example, and so much more. So we're going to go into examples on chemical systems on this video or on this channel. If that's something you're interested in, please hit the like and subscribe button. If it's not something you're interested in, please still hit the like and subscribe button, and you'll be able to see a lot more videos coming out on quantum chromodynamics, twistor theory, tensors, general relativity, quantum field theory, and so much more. So with that being said, I'll see you guys in the next video. Bye.